Today I begin with a problem I proposed to myself, which was, look, Adrian, there is a stream. It could be a river, it could be blood, a stream that starts at this point and arrives at a distance called L, meaning the length is fixed. Not the length, but the distance is fixed. And this particular fluid, we'll assume is commonly done today, that the fluid is Newtonian, meaning it has viscosity. All these things that you learned in fluid mechanics remain, they are good, we keep them. We explore or entertain the question of why is that discipline useful? That is the purpose here in this course. And the flow from here to the other end, from inlet to outlet, inhabits a volume which is fixed. L is fixed. And the question, according to the Constructal Law, is what shape should this volume have so that the access from left to right is the easiest? And this is how, meaning if you pose the question this way, you become acquainted with the challenge. The challenge is that, look, you're freedom, to imagine any possible flow shape from left to right. And here's a possibility, in fact, if you look at these days, you can see all sorts of things on Earth. The maps, the configurations of rivers and river confluences and the deltas and all that. One that's puzzling to some is the braiding of rivers. They kind of start as a delta and then they come together as a river basin, and then maybe like this. Anyway, these will be the paths, you see. Branching and then pairing all together. And each channel has a volume. I'll sketch something that looks like a volume all along. And altogether, those sausages amount to this volume written here as VOL. So there's an infinity of such sketches. From that infinity, some of them must be providing easier access. The first move, which I'll teach shortly, is that, look, if you have two channels conveying fluid from left to right, it is easier for the flow to proceed through a single channel, not through two in parallel. In other words, two of those are worse than one that has a volume that equals the sum of the first two. And this idea, which I'll demonstrate with basically for as if for beginners, because we're in the beginning of the course, meaning that easier is from 2 to 1. It's called economies of scale. So economies of scale is not an empirical observation that rules or underpins economics. It is physics. So economies of scale. So the result of this first aha is that this drawing, from this infinity of drawings, the class that's superior looks like this. From one end to the other, a single tube or channel that's wider. And now this is the class that just won the competition in which this infinity participated. This class contains an infinite number of such drawings. I taught in my previous course the meaning of infinity. It's personal. It's a confession from the speaker. So it should be a confession from the speaker, except that the speaker does not confess. The speaker throws at you the word and the symbol infinity. No, infinity means I do not know, because I'm asking you how large is the number of such drawings. The only answer from the person who questions himself is I don't know. It is not infinite means without end. No, it's it's not in my grasp, you see. But clearly, in this group of winners, there's one that's the best, the one that provides easiest access. That one is the straight tube, because straight, according to Euclid, is the shortest line between 2 points. So the next, this is, so I take you from one cry of victory to another, and this is the result up to this point. It is a straight duct with a cross-sectional area A and wetted perimeter P. And I already joked about the fact that A stands for area, but also for the word any, meaning that the shape of that cross-section, or for that matter, the length of the wetted perimeter, could be anything. In other words, at this step in our climb to perfection in answering, we're still stuck with an infinity of designs. All right? And the next move, to which I alluded more than once in the first 3 lectures, is that when you look at a cross-section, for example, one like this, that would be A. The flow is perpendicular to the blackboard, and the fluid gets stuck or pinched, or obviously brought to rest, which means the wetted wall poses highest resistance in sharp corners. So these are features. You can call them bad. I wouldn't, because what's bad for one design may be useful for another. In any case, they are not good for access. So that's reduced access. And with this final observation in mind, you arrive at the fact that the cross-section should look regular, roundish, to have open corners. And all those cross-sections, once again, an infinity of their own, are called regular polygons. So this is the regular polygon with 6 sides, but n could be anything, all the way to the so-called infinity, which means the perfectly round circle. See that? So, from anything here through various checkpoints on the way to greater access, we arrive here. All right? Okay. How permissive to flow are these straight ducts with regular polygonal cross-section? Well, let's find out, because we have the proper formulas from the blackboard. The so-called access when it comes to fluid flow through a duct. The word access, of course, is personal. You pay for it, meaning you pay for the lack of access. You pay with money for pumping power. And when the flow rate is required, say like the air to the lungs or the blood through the circulatory system, you you pay in proportion to the measured pressure drop or the excess pressure that's needed to drive the flow. So the formula that I put on the blackboard more than once is general for all flow regimes. I wrote it as F. This is dimensionless friction factor 4 times duct length L divided by the hydraulic diameter, and then 1/2 rho, and then the average velocity through the cross-section squared, where the average velocity is the mass flow rate divided by rho and the cross-sectional area. And the friction factor depends on flow regime, laminar or turbulent. We'll see how it does. In the beginning, we will focus on laminar flow. It's the oldest when it comes to flow through ducts and fluid mechanics. So first, the laminar flow. And for laminar flow, famous is the friction factor for a round tube, which is 16 over the Reynolds number based on the tube diameter. And for the other extreme, which is the flow through a slit perpendicular to the blackboard like this, is a 24 over the Reynolds number based on the hydraulic diameter, where the hydraulic diameter is twice the slit spacing. These are items of review. And so we make by the way, this number that resides on top is known as the Poiseuille number. So if you make these substitutions, meaning you replace F with Poiseuille divided by hydraulic diameter, you arrive at all these things. Suggests that the pressure drop is proportional to 1 over the hydraulic diameter squared. And you deal with the hydraulic diameter squared by invoking its definition, which is 4a over p, in this case squared. So these are the substitutions that you make. They're useful. To go through substitutions that are familiar to you may may feel boring. Never think that way. It's good exercise. It enhances your dexterity. Your dexterity, meaning it's like growing into your own shoes. They may feel tight when you buy them, but later they're very, very useful because you don't even have to think about them. The punchline or the bottom line is that the object of the game, I'll just put dollar signs on top, divided by the mass flow rate. You can think of this as a flow resistance, if you want to think that way, is equal to nu L over 8 volume squared. By the way, this L is to power 3. And that gives me a chance to correct the textbook. In the textbook, the exponent 3 was missing. So this is a DCT error. Correct as 3, not 1. All right, so we end up with this multiplied by a group called the Poiseuille number, wetted perimeter, divided by the area. And I wrote it this way. It's like sifting the flour. To separate the flour from, it's called the chaff, is that the word? The one you feed to the chickens. To the left of this bar are items that are fixed. To the right is a group that depends on the shape of the cross-section. So this group is, let's say, design dependent. This group speaks of you, speaks of how clever you are, you see. That's you here. All right, so we continue with you. How does this group depend on the the kind of regular polygon you choose? The next step is kind of pedestrian. I made a table of how this group depends on n, the number of sides of the regular polygon. So we have n here, and that group, which is Poiseuille wetted perimeter divided by a. 3 means equilateral triangle. And the number that you get here, dimensionless, has to be dimensionless. Look, meter squared divided by meter squared. It's really nice when things turn out to be dimensionless, you know. I could make fun of you. I could say here 277.1 kilograms, you know, and see whether any of you catches the joke. No, it's dimensionless. Okay, if it is square, the number is phenomenally very close. All right, there are some other such numbers in the textbook, but the 6, of course, you saw is the hexagon. That's 208 0.6, all the way to the alleged infinity for the value of n. And in that case, limiting case, the number is 201.1. They're all very close. Everything that flows through a regular polygon competes with the so-called perfect. Yeah, how about that? It's like, yeah, what?
What about like a slit?
Louder?
What about like a slit? So n equals 2.
Yeah, but the slit is not a regular polygon. We already know that the slit is inferior to this class. But it's a pretty good question, because you could have slits that are really, really slitty, very, 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 what do you call them, slender in cross-section. You could also have slits that are kind of fat-looking. So here's one slit. But here's another one that performs nearly the same as the, and then you could have a ellipse. The ellipse is obviously between the slit and the round cross-section. You can play these games. This is very useful, and to educate or to improve your senses. I'm talking about the way you think. To liberate the arrival of your new thoughts, you see. Why not plot these numbers on a graph? I said to myself. In 2 dimensions means on the abscissa I plot the figure of lack of merit. That would be something that's proportional to Poisson number p squared divided by a, meaning poor access. And on the ordinate, I plotted the inverse of my freedom to make the drawing, 1 over n, meaning when n increases, my hand has more freedom to move on the piece of paper. So n means greater means freedom. And clearly, the circle scores the smallest value of this, but then all the other ones constitute a constellation of such points upward toward smaller n. This hexagon is here, up and slightly to the right, then the square, and the triangle. And these are the champions of cross-sections. It is not a continuous line. It is more like the sequence of guard towers that mark the frontier of a totalitarian state. If they could not plant landmines, they planted these people with machine guns at the top of tall wooden structures. But it is a kind of a frontier, a kind of a boundary that separates one territory from the rest. So if this is the so-called territory of the perfect, well, that point, help me with the English. Is it the point like where in French, the method is called pointilliste, a drawing made of points, not of a continuous line. You get the idea, okay? To the right of it is the world of possible cross-sections. Not as good as the regular polygon, but possible. I'll show you if this for n equals 4, you could have quadrilateral cross-sections, maybe this way, or trapezoidal, and so on, with 4 sides, but not a regular polygon. And their values on the abscissa would be greater than the value of the champion with n equals 4. So, to the right of the guard towers, watchtowers, you have the domain of the possible. The rest of the so-called kingdom of designs is the impossible. Use your imagination. You haven't had thermodynamics yet, right? Yeah, but keep this in mind when they teach you about the very famous efficiency of Carnot. That is one boundary of a so-called perfection that separates us mortals from the impossible. But with a drawing like this, you see the usefulness in this particular course. It empowers you to see from the course, not from looking around, the existence, to predict with the powers of your mental viewings, to predict the existence of perfection, but to approach that with a humility that not even the regular polygon as a cross-section can be manufactured. There's always an imperfection in manufacturing, and that includes the round cross-section. Even if it is made perfect according to today's techniques of manufacturing, as soon as water starts flowing through that duct, that flow deposits gunk on the surface, and on and on and on, okay? So, this is a big thing here. The fact that that there is a population of designs, a diversity of designs that perform nearly as well as the perfect design. So you discover diversity as belonging in nature. I call it natural diversity. And of course, this would be perfection. It's okay to know it. It's also okay to think of it with humility and to allow for the fact that it may be beyond your reach. PO is the saluting the contribution of Poiseuille. A medical doctor in 1830 who, in his own way, because by this time people knew calculus, predicted the formula that later was written as F equals 16 over the Reynolds number based on hydraulic diameter. And I have so that is the meaning of the Poiseuille number. the solutions for, meaning the special case of this general formula for every postulated cross-section end up being written this way with a special expression for the friction factor, meaning in retrospect, in today's age. So the whole body of fluid mechanics is summarized this way with a diversity of expressions for F because the cross-sectional shapes are diverse. So what I teach first is the general formula. In today's lecture, I answer your question, which is what is F? F is a very useful idea because these expressions for F are simple. And as you'll see in the case of turbulent flow, F is a constant. That's even better, you see.